These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. Well, why don't we try question 57 on page 29. Question 57. And our goal here is to take a systematic approach to this. Well, we already started talking about the systematic approach last week, so let's try to use that as much as we can, and then maybe we'll find some other things that are helpful. So we'll try question 57. If you have, do you guys still have the handouts that I gave you last time?
Yes.
You have those with you? Page 29. So remember that the systematic method is also on those handouts, so it might help to refer to that while you're trying problems. let's talk about that a little before we go on to part B. We want to kind of try to use the systematic approach from the handout. So we want to actually physically draw the object's path. So we might say that here we have the wall of snow, and we have a hockey puck that's going through that wall of snow. We want to try to build as much information as we can into the hockey puck. So we want to say that when it enters, it's moving at 32 meters per second. And remember, we want to get in the habit of always putting in signs. Well, we might as well assume this is the positive direction, which means that we've already chosen this to be our positive direction. It's 35 centimeters thick. And I think you all noticed that that was not consistent with this unit here. This is in meters, so the distance has to be in meters. We might as well make that conversion at the start, otherwise we might forget it. Well, if we have 35 centimeters, what conversion are we going to use?
100 centimeters in 1 meter.
Right. Or you could do 1/100th of a meter in 1 centimeter, but this is maybe more straightforward. Well, because this has 2 zeros, we're moving the decimal point 2 places to the left. One of you might have moved it 3. We want to move it 2 places to the left. And that would give us 0.35 meters. And I'm going to put a positive sign here too, because we're moving in the positive direction. People oftentimes forget that displacement can be positive and negative as well, but that's also a vector. So I'll say that we're moving 0.35 meters in that direction. It emerges moving at 18 meters per second, and again, that would be positive 18 meters per second. So again, take the time to build as much information as you can into the sketch. This problem was maybe a little bit easy for a warm-up, but that's one good way to have a better idea for any problem that you're working on. Make a big sketch and build all your information into the sketch. Anything else the handout says to do? Label the initial and final positions. Well, here's our initial position, and here's our final position when we enter and leave the wall of snow. One thing I think you might not have done was drawn the velocity and acceleration vectors. Maybe that wasn't a big deal here, but it's a good habit to get into. What direction is the velocity vector in? To the right. And what direction is the acceleration vector in? Yeah, how do we know? From our common sense. We know that the snow is going to slow us down. And we saw last time that when you're slowing down, the acceleration is opposite to your velocity. That wasn't very important on this particular problem, but it's a really good habit to get into to actually draw the velocity and acceleration vectors. All right, step 2 is to write down our positive direction, but we already had to do that to get our sign, so we've already done that. Step 3 is to break things into components, but that's not necessary for one-dimensional motion, although you might have started learning about that in class as you move into 2-dimensional motion, or maybe you haven't quite got to that. You should get in that next class. Step 4, write down all the kinematics variables. And this was a step that you guys kind of skipped. I mean, you were writing down the variables, but I didn't see that you were writing them down in one place. It's a good idea to start, or maybe you didn't, I just didn't see it, but it's a good idea to actually physically write down just in one place on your piece of paper, all 5 of the kinematics variables. That's going to be our basic framework for attacking the whole problem. Anytime we get stuck, we should come back to here and see what we know and what we need to figure out. So it's a good idea to actually write these physically out. So here's our kinematics variables. And then we should use a question mark to indicate what the question is asking us for. The question here was asking us for the time. So I'll put in that question mark. And then write what we know. And at this step, I don't think gave you much trouble. So this was positive 32 meters per second. V final is positive 18 meters per second. The displacement is positive 35 meters. Again, the displacement has a positive sign. And once we have 3 numbers, we're ready to pick out an equation. It looked like you all picked out the right equation. You picked the equation that was missing the acceleration. So you can easily pick that out from the handout, just going down the column and seeing who's missing the acceleration. So we have displacement equals V initial plus V final over 2. Remember that this, with constant acceleration, this is just the average rate. So this is just distance equals average rate times time. Positive 0.35 meters equals positive 32 meters per second plus positive 18 meters per second over 2 times the time. And then you solve this by algebra, and what answer did you get?
0.014 seconds.
I think that's what I got too, so that looks good. Okay, so I think, except for maybe for one little problem with the units, you all did well in getting through this problem. It wasn't too confusing, but it is a good idea to actually write down all 5 of these variables in one place. That helps us to avoid getting confused on more complicated problems.